Okay, great. Well, thank you very much for invitation to this very stimulating event. I'm not the mathematician, I'm not material scientist, but hopefully can find common ground that we're all interested. So I originally didn't put the rigid in this title, but I think my main message is soft, rigid, complex robots, so that hopefully fit to the topic of this seminar. Okay, so the problem we're working on, let me start with first video here. So we are interested in agri-food industry. So this is one of the companies we are working with at the moment. The GS Growers, a 30-minute drive from here. They're producing 2 million lettuces every week. It's #1 producer of vegetables in the UK, and in this particular video, they're harvesting lettuces. So everything is automated, but the last 1 meter, like harvesting, trimming, inspecting, and the placing, or wrapping and placing, all this little last thing was not automated. So that's why they came to us, and how we can solve this kind of problem. And everything do it in 5 to 10 seconds, and this is something that we cannot really solve in robotics at the moment. And we want to show another example. This is again the 30 minutes drive from here. This is a beetroot cooking factory. These humans are kind of in a really difficult situation, standing there 9 to 5 and inspecting and trimming a beetroot every day. It's not really favorable environment because it's smelly, it's humid, high temperature because they're just cooked by vinegar after this. So this is again look like an easy problem, but it's not quite easy for robotics. So that's another thing we're working on. And this one is a little more complicated. This is a bouquet making factory. Again, 30 minutes from here. The flowers are made in South Africa and South America, but the bouquet has to be made the last minute in England, and they are kind of very complicated manual tasks that the humans doing. So the problem here is the temperatures. The flowers don't like high temperature, so they have to sit in 3 degrees Celsius even in the hottest summer, which is not designed for human workers, obviously, right? And more difficult thing for this problem is that the flowers can be sold only 4 times a year. Valentine's Day, Mother's Day, Easter, and Christmas. Right, the 4 times, and these people, most of these people lose this job for other days, and they are doing completely different kind of things apart from these 4 peaks in the year. So again, this kind of thing is not really jobs for humans, but there's no real technological solution to solve this problem at the moment. So we're kind of engineering trying to solve all these problems in the real world, and we're trying to find out what actually the problem, right? And of course, this is actually the problem. Most of the workers from Central Europe or Eastern Europe. Hopefully, I don't have to use this slide in a couple of weeks' time. But this is significant problem at the moment, and we actually all these farmers and the food manufacturer came to us to give them a solution. So we actually started thinking about what's technological problem apart from political and other problems. So robot manipulation is not a solved problem, right? So this is known as still a grand challenge for robotics. So robots can go to the Mars, so robots can go inside our body, but robots cannot pick up the keys from the pocket, right? So this is a really difficult challenge. And there are many associated reasons because on this problem. The first one is the cost, right? So the cost human is about £10 per hour. In the UK, it's a little lower than this, and it's very difficult to build robots for this price of the job. And then on top of that, we have dexterity in the motor control. So the harvesters do cut, trim, inspect, wrap in 5 seconds. This is not really an easy problem for robotics. Sensing is another one, so it's not only a visual computer vision problem, but there are a lot of problems related to the tactile sensing. And finally, the physical contact turns out to be a really difficult challenge because the robot has to be physically in contact with objects, and we need to have some sort of mechanism for self-healing or disposal things. And in the end, the creativity. So every product, every weather, every situation is different. So robot has to somehow deal with this variation of situations every time. And all these things are still, each single individual of this problem are rather, manageable, but if you have to put them together with a reasonable cost, it's not a really easy problem. And that's why we're really interested in exploring new kind of materials so that we can, approach this problem of robotics in completely different ways. And that's the kind of background of our research project. So what do we mean by using smart materials in robotics? I just want to give you one example of this kind. It's called the universal gripper. So this is the robotic project explored in the US. That this robotic end effector is made of a balloon filled with ground coffee. It's very different from conventional robots in the sense that robot is deformable, right? So it's a balloon inflated, can be conformed to any different kind of materials if it's in physical contact. But as soon as you apply vacuum, then you can pressurize the contact point so that you can pick up the different kind of object without really explicitly controlling the body of the system. So, material plays a very important role in this kind of scenario, and that's kind of one interesting approach to really think about how to build robots in a different way based on the material properties. So if you look at the mechanism behind this, the important mechanism here is the so-called particle jamming. So there's a lot of particles inside the gripper that plays a really important role to do phase transition between soft and hard structure. And then when it's physically in contact with the object in front of it, the structure automatically fits to with the object. So if you want to calculate the force between this object and gripper, there's nothing really complicated math. It's just calculating the force, sucking force and the friction force. This is the sum of these are the gripping force of the object, and all these things can be kind of deduced by thinking about the physical principles. But the really important thing is that all these equations don't need to be known for the robots. What robot is doing is on and off the vacuum. That's it, right? Everything else is kind of taken care by the material properties interacting physically with objects. So that's the kind of new way of thinking about how robots can be intelligent by taking advantage of materials and the physical interaction with the environment. So our kind of big picture of research is what we call the embodied intelligence. Usually, robotics is thinking about task environment and make some sort of mechanical structures and then design the controller so that robot can be intelligent. But what's actually really important is what's in between, how we can design mechanical structures and the material properties so that they can have a good interactions to reduce down the control efforts of the system. So we are actually looking at the mechanical system, how action of the robot can lead to interesting interaction with the environment, but also mechanical aspect of sensing, how sensor can be mechanically designed for the better the interactions. So we talk about soft material at the beginning, but the softness is not enough. We just need to think about the mixture of soft and rigid complex structures. Most of the robots, conventional machines, conventional robots use rigid materials, gigapascal order, in aluminum or plastics and so on. But if you look at biological systems, 90% of our body is usually kilopascal or megapascal or the Young's modulus. So there must be something completely wrong with the way how we build conventional robots, compared to biological systems. So that's the kind of inspiration we get from biology, how we can build robots in a different way by using softer materials. So why soft material important? The soft material is good because it can give a lot of flexibility and large degrees of freedom just by shown in the universal grid power. Just by having soft structures, you have a very good interaction with the environment. But on the other hand, there's a drawback of soft structure is that you cannot really transmit large force. So if you cannot exert force on the structure, you cannot do precise control or strong control or scaling up to the bigger system and so on. So the rigid robot is also a good aspect of it. But I think that's a really important principle, but we just have to somehow do the mixture of soft and rigid structures in a clever way. So a lot of people use in industry rigid manipulator like this. More recently, researchers started looking at the soft manipulator like this. But what we really need for dexterous manipulation is somewhere in between and how we can put them together. So that's the kind of motivation we started a couple of years ago. But it's not an easy problem because if you look at our body, it's really, really complex mixture of the rigid and soft materials. So we started just copying nature. Just downloaded some CAD model of human skeleton and put them together with elastic ligament and tendons and so on. So with just handcrafted, really complicated anatomically correct structure to begin with. And so this gives a really good passive dynamics of the structure. But it turns out that the control of such a structure is really difficult. So if you look at our tendon system, just to control 2.5 fingers, we need 14 muscles to do it. So we actually put the 14 muscle electric motor at the bottom of this platform and see how robots can actually do interesting interactions with the objects in hand. So it already shows some form of natural interaction with the object, but the control of this is not acceptable if you want to do commercialize anything. So we started interested in other aspects of it. So one of them is the actuation problem. So a lot of you working on artificial muscles and so on, but I think this is a very, very important, crucial area. So one of the things we are looking at is how the soft structure can be actuated by using a Bowden mechanism. So basically, we have soft continuum structure like this. And these are connected through tendons pulled by electric motor. But then depending on how you place the pulley mechanism on the structure, you can actually do quite interesting behavior variation just by having 1 or 2 actuators. So we actually don't need so many actuators even if you have a very complex soft structure. But we have to kind of carefully thinking about how to put the actuators and the tendons and pulleys in the structure. So that's one aspect we looked at. And one of my students previously think about how to do chopsticks with soft robot hand because chopsticks is not easy, well actually it's not possible for conventional robots and even for humans, especially European, right? It's not really good at the chopsticks. But it turns out we actually need 1 or 2 actuators to control the position and the force of the chopsticks if you have chopsticks placed in the right location. What's really difficult is how to hold the chopsticks, right? Going to that configuration is a very difficult challenge, but once you have chopsticks in your hand, it's actually very simple control problems, and that's what we call muscle synergy principle, that we have so many muscles, but we are not controlling all these different muscles independently, but many of them are kind of pulled together, and that's a very important concept for soft robotics actuations, and that's something we are exploring at the moment in our laboratory. And then another thing we are looking at is the 3D print, multi-material 3D printers. That's quite available many places in the lab. So we started exploring how we can use this new technologies for making really, really complex soft robots. So that's again, we made the skeleton hand based on multi-material. In this case, we use two materials, relatively rigid materials and relatively soft materials, and then we can actually print seamlessly, changing the material properties of the bones and ligaments together, and see how this kind of structure can help interacting better with the environment. So the challenge we worked on, well, let's see, there's no sound. Oop. Okay. It's not greatest pianist yet, but I hope you get some ideas about what we're trying to do. So what we're trying to do here is actually trying to control the wrist by using robotic arm and see how this skeleton hand, robotic hand, can actually interact better with the environment, in this case the piano. But what's really interesting about this problem is that the mechanical structure of skeleton can be very complicated. So here, this is the kind of, I think this is the first finger, just copying the nature exactly with the bones and the ligament, and then measure the elasticity on all different directions. The important thing is that we can actually change the material properties, especially the ligament part is very crucial. So we try different mixture of the softer materials in the ligament and see the elasticity profile can change across different directions. So in this particular case, if you want to play one finger note, we still have to think about lots of things. We just have to think about something like the speed of the pressing, or articulation or volume. All of these things are kind of very important if you want to play a music like this. But in this case, we actually need a very rigid finger, right? So we need a rigid on this direction because that's how we actually do it. And piano is designed for it. But the other kind of problems, like this problem, right? So this is the thumb abduction and adduction. So here we need the direction, rigid direction in a rigid property in one direction, but we want to make it softer in the other direction. So the thumb finger is actually very difficult to design, but actually we managed to get this design done such that the finger can play a note like this. So we kind of try to explore how multi-material 3D printer can be used to design complex systems, but at the moment we're just doing a lot of trial and errors and just copying the nature to see what is actually possible and what is not possible at the moment. But this is the kind of place where we can do active collaboration with the modeling of mathematical modeling of design as well as materials and the robot control problem. So I don't have much time left, but I just want to do just one little another project we are working on. So what we are really interested in is how design of the robot can be made by robot itself. So if you look at ourselves, we start with one single cells and we go become a really enormously complicated robot. So we're exploring how this kind of process can be possible in robotic system by taking advantage of new materials. So one of the projects we have been exploring is the use of this thermoplastic adhesive. So by equipping the hot glue gun in the end effector robotic arm, robot can actually do 3D printing as well as assembling of parts together by using a bonding method. So this robot is making a cup and the stick by gluing them together so that we can make a kind of structure like scoop. And then robot can use this structure to do transportation of different kind of materials. So here a scoop can transport water, or robot can also make tweezers of large tweezer, smaller tweezer, and so on. So this is a kind of interesting tools to explore how robot can autonomously change its own shape actively. Of course, the design here is given by humans, but significant, interesting research is how robot can actually design its own body automatically. But again, the important thing here is the material. So we use a hot melt adhesive, so it's very well engineered material that can change adhesiveness and the transition temperature quite well controlled. So we actually using this material for many different kind of problems in our laboratory to deal with different kind of problems. So one of the problems we are working on is the sensor morphology. So if you look at nature, animals have all sort of different kind of mechanical structures for sensing purposes. So how the new kind of the 3D printing technology can be used for robots to change the sensor morphology. So how robot can actually change the structure for the purpose of filtering, amplifying, and the converting signals. So what the experiment that we did is the same setup here, with the robotic arm equipped with a camera in this case. So let's see how this robot is doing. So robot is making stick-like structures, and that is connected to an end effector, and then this stick can be used as a whiskers to interact with the object, and then the camera is looking at the interaction of the structure with the object, and then depending on how the structure is bent, robot can actually perceive the stiffness or softness of the structure of the object. Another example here is the temperature sensing, right? So because this thermoplastic is sensitive to temperature, these materials can be used to measure the temperature of object just by touching it and see how the object drops down, and so on. So this is very proof of concept type research. But the interesting thing is that the mechanical structure can actually give a lot of influence the way how robot can perceive the world. So in this case, we focus on the force sensing and the temperature sensing. But the benefit of changing mechanical structure is actually sensing of different kind of physical stimuli, as well as changing the sensitivity and the sensing range of the object you're touching. So we actually have a modeling of how sensing range and sensitivity can be changed depending on the morphology of the robot. And then we actually see the trade-off between sensing range and sensing sensitivity. And the same with the temperature sensor. Okay, so I think time is up. So just very, very briefly, I'm very excited about talking about the soft, rigid, complex robots, which is, I think, in my opinion, is the grand challenge of robotics. And I have done very little about mathematical design of all these case studies. But there are lots of interesting issues about soft rigid phase transition and the materials for sensing, material for actuation. All these things are kind of interesting avenue for research in the future. Just to give a bit of advertisement, we're starting up the CDT on agri-food robotics, and we have a lot of students available for this. So if you have any interesting project associated to robotics, please let me know, and I think this is going to be interesting place for interdisciplinary collaborations. Also, we are issuing the newsletter on soft robotics community, over 750 members. And if you go to softrobotics.org, you can receive the free newsletter every other month, what's going on in the field of soft robotics. With this, I'd like to stop my presentation. Thank you very much. Yes.
What is the major challenge? Is it to make the hand or is it to control it?
Make the hand and control. I think they are all coupled together, right? Because if you have a good hand, control is easier. If you have a bad hand, you cannot control it. So in the end, we need a kind of control. But I think making of hand, what we need is basically pulling one actuator here and automatically adapt to the structure in a good way. So that's the kind of thing we're trying to look at, and that's what we call as bio-inspired design of robotic hands. Yes?
With temperature and mechanical properties, you seem to be using contact-based methods to assess those. I mean, couldn't you measure the temperature just with an infrared beam or the mechanical properties acoustically or something? Why do you need to contact the object?
Well, I think we're interested in kind of sense of touch for robots, because what we do is we measure a lot of things by touching, and we don't want to have all different kind of mechanism to sense different kind of things, because what we need in the end is the crazy robot that can do everything, right? So how we can mechanize all this different kind of sensor modality in fingers. And that's the kind of ultimate goal we're heading to. But if you want to have an engineering solution, why not just having many different kinds of sensors, different places? But we cannot afford this cost for cheap problems like agriculture. Yep. Yes.
You seem to be focusing mostly on the structure of these devices, hands in particular, with these materials. What about the actuator side? Where do you see that coming? Because at the moment we've got electric motors and they're pretty useless for this. And
so yes.
Else is picking up the slack.
So soft robotics is suffering from the actuation technology at the moment. There are two major approaches. One of them is a pneumatic, and the other one is the tendon-driven, like what we did. There's no other solutions roboticists can easily use. Of course, there are lots of artificial muscle research going on, but many of them are still suffering how to put them together into integrated system that can work robustly. So I think that's definitely one of the really big area that we have to solve in the coming years.
Can you say any more about the best tendon materials as well?
Tendon materials are a very interesting one as well. Yes, we're using fishing line. We try many different kind of things, but one of the challenges is how to have the tendon that doesn't stretch too much while not having the friction. So that's also a lot of know-how packed in that place, but absolutely, this is another interesting area that we want to measure the sensing, the force through the tendons. Ultimately, that's what we do in our tendon and the muscle system. So that's absolutely another interesting research area. Okay, thank you very much.